Good morning. Today we come to the last lecture of this week, or the last lecture of the clustering, in fact the last lecture of this class. We will talk about hierarchical clustering. Rather, we talk about a specific bottom up hierarchical clustering algorithm. Earlier we have seen k-means algorithm, which is an example of a top down clustering method. Today we will look at a bottom up clustering method. Now, hierarchical clustering is very common. For example, when scientists look at the animal kingdom, they divide them hierarchically. Animals as vertebrates and invertebrate, within vertebrate you have fish, reptile, amphibians, mammals and so on. So, this produces a nested sequence of clusters. So, we can, in order to get a hierarchical cluster, we can recursively use a partitional clustering algorithm like k-means. We discussed the k-means algorithm in the last class, and the k-means algorithm can be recursively used to do a hierarchical clustering. But today we will talk about a bottom-up clustering method called agglomerative clustering. In agglomerative clustering, we build the clusters from the bottom level. That is, we assume that every object, initially we are given m objects, we assume that every object is a cluster of its own. Then what we do is we find the distance between each pair of clusters, and those clusters, that pair which is closest to each other is merged, so that at the next step we have m minus 1 clusters. Again, we try to find the closest clusters and merge, so that we have m minus 2 clusters. Like this we go on until all the clusters are merged. So, this is the gist of agglomerative hierarchical clustering. We could also use divisive clustering to make hierarchical clusters. We can start with all data in one cluster, take k equal to 2, divide it into 2 clusters. Then each cluster we can recursively keep dividing. So, this gives us top down hierarchical clustering. However, we will not discuss it further in this class. Now, the bottom up hierarchical clustering gives rise to a structure called the dendrogram. So, what is happening is that if you have the different objects, suppose these two objects are the most similar to each other, they are merged at step 1. Then step 2, the next most similar objects are merged. So, this is step 1, this is step 2, and then step 3, the next most similar objects are merged. So, let us say this is step 3. Step 4, the next most similar objects are merged. In step 5, the next most similar objects are merged. Step 3, the next most similar objects are merged. In the step 7, the next most similar objects are merged. So, this structure gives rise to a tree which we call dendrogram. And as we see in that, in the dendrogram, the nodes represent the subsets of S. So, this is a node, this represents these 3 points. This node represents these 6 points. This node represents these 3 points. So, each node represents a subset of the points. And the characteristics of the tree is that the root is the whole input set. The root of the tree is the entire set, and the leaves are the individual elements, and the internal nodes are defined as the union of their children. We can also represent this by this sort of diagram, right. So, this is the one cluster, this is another cluster, this is a nested cluster, these are nested clusters. So, the objects are hierarchically nested, which can be represented like this sort of a set diagram or this sort of a dendrogram. So, this tree may be cut at different levels. If you cut at this level, you get only one cluster if you cut at the root. If you cut at a particular level, this will give you a certain number of clusters. For example, this cut gives you 1, 2, 3, 4 clusters. This cut gives you 1, 2, 3, 4, 5, 6 clusters. So, cutting the dendrogram at different levels, you get different numbers of clusters. So, you need not decide the number of clusters a priori. You can construct the dendrogram and cut it at the desired level to get the number of clusters that you require. So, for different values of k, you get different clusters, as is illustrated by this picture. So, the algorithm is notionally very simple. The basic algorithm is very simple. Initially, each data point forms a cluster. We compute the distance or proximity matrix between the clusters, and we repeat the following steps. We merge the two closest clusters. After merging, we update the distance matrix, and we continue these two steps until we get only a single cluster. Now, the main thing about this algorithm is the distance measure. Depending on different definitions of the distance will give us different algorithms. Now, initial step is every point. So, this is the set of objects. Initially, every object is a cluster by itself. So, every point is a cluster, and if there are m points, we have a m by n proximity matrix between each pair. So, there will be m square pairs. Between each pair, we can compute the distance and fill it up in this matrix. Then, at an intermediate state, we would have a number of clusters, and the proximity matrix will be defined. Suppose there are k clusters, there will be k square elements in the proximity matrix. Now, suppose in this matrix C2 and C5, so we have this proximity matrix, and we compute, we find the distance between these 5 C2 pairs, and suppose we find C2 and C5 are the closest. Now, what we will do is that we will merge C2 and C5, so that these two columns and these two rows in the proximity matrix will be collapsed into one row, one column. So, the next step we will have 4 clusters. So, 4 rows and 4 columns in the proximity matrix. So, after merging, we will get these 4 rows and 4 columns, and we have to find out how to fill up this column and this row. Now, how we fill up will depend on the distance measure that we will use, and we will talk about certain common measures that we use for this. Now, when we have to find the closest pair, as we said that there are different ways to measure distance of two clusters. Some popular methods are single link, complete link, average link, centroid. In single link clustering, when we combine two clusters, when we look at the similarity between two clusters, suppose we have cluster Ci and cluster Cj. So, we have cluster Ci comprising of the points x1, x2, and cluster Cj comprising x3, x4, x5, right. Now, what is the distance between Ci and Cj? We find the similarity of x1 with x3, x1 with x4, x1 with x5, x2 with x3, x4 and x5, and we find that pair which is the most similar, among a pair, we find that pair which so that one of them belongs here, one of them belongs here, and we take the most similar pair. The similarity of the most similar pair we take as the similarity between the two clusters in single link clustering. In complete link, which we will talk next, we take the least similar pair as a measure of the similarity between two clusters. When we take the similarity between two clusters in single link, we take the value of the similarity between the most similar pair. In complete link, we take the similarity as the value of the least similar pair. In average link, we take the average of their similarity, and in centroid, we take this to be represented by its centroid, this to be represented by its centroid, and look at the similarity between the two centroids. So, in single link, the distance between clusters Ci and Cj is the minimum distance between any object in Ci and any object in Cj, or maximum similarity of one object in Ci with one object in Cj, which is given by this formula. Sim Ci Cj equal to max x belongs to Ci, y belongs to Cj, sim x y. So, for an example, if these are the points in single link, we will take the most similar points, then the next most similar points, and so on, and then combine them. So, as we see that single link clustering can result in straggly, that is long and thin clusters due to chaining effect. Next, we look at, so in single link clustering, the similarity is determined by one pair of points, that is one link in the proximity graph. So, if the proximity graph has these values, so what we need to do is that we have to look at the most similar pair and merge them. In a complete link method, on the other hand, the distance between two clusters is the distance between the least similar pair. So, which is given by the following formula: sim of Ci Cj is min x included in Ci, y included in Cj, sim x y. And complete link makes tighter, more spherical clusters, right, unlike single link where you can have long, thin clusters. However, complete link clustering is sensitive to outliers because they are far away. So, if there is one object in a cluster which is very far away from the other objects, it will influence the similarity, which is not always desirable. Again, you have this matrix and you look at, you can apply complete link. On the same example as we saw before, we can show that when we apply complete link, these are the different steps that we get. We notice that here the clusters are more tight than what we get in the single link example. Now, let us discuss the computational complexity of the clustering methods. So, hierarchical agglomerative clustering method, in the first step, you need to find similarity of the objects. If there are n objects, you require to find n square similarity in the beginning. Then you have n minus 1 steps. So, in each step, you are merging the clusters, and while merging, you have to find out the most similar pair and update. Now, how much time you spend will depend on the type of clustering method that you are using, single link, complete link, average link or centroid based, and it also depends on the type of data structure that you maintain. So, if you naively do this, usually it is order of n cube, but in certain cases you can also achieve n square log n complexity. We will not describe the details. Okay, so, we talked about single link and complete link. In average link clustering, actually average link there people have described in two different ways. You can average across all ordered pairs in the merged cluster or over all pairs between the two original clusters. The second formulation is shown here, but there are other formulations of average link clustering. So, anyway, here we find similarity of clusters Ci and Cj is average of similarity of xy, where x belongs to Ci, y belongs to Cj. It is a compromise between single and complete link. It is less susceptible to noise and less susceptible to outliers. It also produces spherical clusters. Complexity we have already talked about. With this, we come to the close of today's lecture. There are other clustering methods like density based clustering, for example, the DB scan algorithm and several others, but we will not talk about this in this course. So, this brings us to the end of the class on clustering and also the end of the course in machine learning. I hope you all have enjoyed this course. Thank you very much for putting up through the entire course. All the best.